So the topic of my thesis is dynamic spectrum management architecture and algorithms for the mobile internet. Quite a mouthful, but I'll try to explain different parts of it the best I can. Before I start, here's the list of problems that I worked on, mainly on two broad topics: dynamic spectrum access and mobility first internet architecture. On the DSA side, I started with looking at Wi-Fi, Bluetooth, Zigbee interference in 2.4 gigahertz and also interference reduction in mobile hotspots. Moved on to self-organizing networks, especially in the field of wireless backhaul architecture during my internship. And of late, I've been looking at something called network collaboration for dynamic spectrum access, and I will go through some more details about this topic. On the mobility first side, I was involved right from the start of the whole architecture, so from the core design of the different components, the distributed name lookup infrastructure, comparison with CCN, and then we looked at mobility first in specific scenarios like vehicular networking, like multi-home devices and so on. Lastly, we looked at how things should behave in specific wireless access scenarios, and we built some management plane services inside mobility first. So this thesis is about the overlap between these two broad kind of topics, and I'll go through how they are related in the next few slides. This is the outline of the talk. I'll first describe my views on the evolution of mobile internet architecture, and then describe what I mean by network collaboration for DSA. I'll go through two detailed use cases for this kind of approach. One is a client AP association problem, the second is channel selection, and lastly I'll describe our ongoing work about how to realize this kind of a cooperative way of doing DSA. So this is the picture which shows the four main components end-to-end in a mobile internet architecture. We have the user device, an access network, the internet, and the hosted services. Now if we look at how these functionalities are broken up in a traditional cellular network architecture, it would look something like this, where there is a lot of functionalities inside the access network. For example, it manages the radio resources, it manages the quality of service, it manages the mobility services, and so on. There is very little that is left for the internet or the hosted services to do. It's essentially just a pipe between the gateway node in the access network and the point where the files are hosted, essentially. The advantage of this kind of architecture, and this has served us well for several years, because it gives a very fine-grained control over the quality of service that the users are experiencing. On the downside though, it has a very high cost in terms of both operational and infrastructure. So what we have been seeing of late is a new kind of architecture where the network is built up of a lot of small access networks which are wireless LAN based, Wi-Fi based. And in this kind of network, the access network itself is very thin. It's nothing more than just the access points and some local coordination for DSA. But apart from that, really everything else is now just a cloud service. For example, there's a cloud service which manages your rates. There's a cloud service which manages the reachability, for example, and so on. Now in this kind of architecture, it's very cheap to deploy, and that's the main reason why we are seeing these kind of deployments. On the downside though, there is now an increased latency in several critical functions that typically we would want them to be of low latency, but because they are hosted all the way inside the internet, it's increased latency. Now, in view of all this, the ideas that we have had in the mobility first architecture looks something like this, where we want to put a little more functionality inside the internet, the core internet itself. Now we are stretching the word internet a little bit here, but I'll try to explain what we mean by that. So in this kind of architecture, what we have is a heterogeneous kind of access network in which it will be built up of both Wi-Fi access points as well as LTE base stations. There will still be functionalities that will have to be done on one end of this pipe, but there is now a lot more functionality that is a part of what the internet does. For example, reachability or mobility management, changing rates depending on the channel characteristics of the clients and so on. The big benefit of this kind of approach is that it reduces the latencies involved quite a bit, and it reduces the duplication of the same services. So the question that comes out of all this is, how do we reason about which functionality should reside at what point? So that's one of the first things we sort of studied in detail. We take each functionality and how do we determine what is the right place for this functionality. And our approach has been to look at some concrete requirements of mobile and wireless access networks. And I'll skip the details of this part, but this was one of the first works we did on this. We looked at these 5 specific scenarios: the mobility of host and networks, the link quality variations, multiple network access, ad hoc networks, and lastly spectrum access coordination. And then as a result of this process, we thought that there are 3 things we should really do inside the network. One is reachability or mobility management. The big benefit here is that it substantially reduces the latency. Second thing is it eliminates the need for each application to do this on its own. For example, if you use both your iMessage as well as WhatsApp, they both have to be informed whenever you change a network right now. But if it's this kind of a reachability is done inside the network, this kind of a duplication can be reduced. And we had a couple of results from this work. The second thing is link quality based adaptation. So anything through which you are trying to adapt the rate in response to changing conditions, we think it should be done as late as possible, deeper inside the network. So if you want to, for example, vary how much traffic is sent on 2 of your interfaces, we have results that show that if it's done inside the network, it's better as compared to done at the sending side itself. So that's one other thing. The third thing, and this is not so obvious thing to do, is we should do a more ingrained support for dynamic spectrum access as a part of what the internet does. So this is what I'll spend most of my time in this talk about. So I'll explain more about this. But before I start on that, let me explain what I mean by spectrum coordination in general. So this is my view of the word essentially. It is any kind of interaction between managed wireless networks over the back-end wired link for increasing the spectrum utilization in a variety of manner. So if we have 2 networks A and B, it means information exchange about both individual devices inside the network and also on an aggregated basis, like what is the technology being used, what is the list of parameters that you are using and what I am using, exchanging this kind of information. And also on an algorithmic point of view, where you would exchange information about what adaptation algorithm are you using, what am I using, and even merge these 2 algorithms to result in a better, more centralized, better kind of a spectrum efficiency. So we looked at 2 very specific scenarios where we tried to answer this question, that what exactly can be improved using spectrum coordination. So the first thing we looked at is client AP association, and the second is channel selection. I'll just go over client AP very briefly, since I think most of you have heard that talk at some point or the other. I'll give more time to the channel selection part. So the first problem first, the basic problem looks like this. We have a Wi-Fi client C1, and we have 3 APs in its range. And based on the distances, these are the throughput, expected throughput that the client will get if it connects to each one of them. Now, in a standard default rule, it will select channel AP1 since it's closest. However, what happens if there is another client already connected to AP2, AP1 is that the channel access time at AP1 is divided into 2. And let's say for simplicity, both require equal amount of data. Then what the client C1 will get is only half of what it expected to get. So in this kind of a scenario, if there was a central controller like the Aruba controller that Ivan is trying to deploy here, it would see that this is happening and it would connect the client C1 to AP2 instead, since now at least it will get 48 Mbps. What it cannot do, however, is detect accurately the presence of a foreign AP client pair. And let's say if this was right next to this AP and it had an identical traffic pattern, in this case what the client will see is half of what it expected, even in this case. So that is the benefit of inter-network information sharing. If we have some kind of a sharing of information, we can make the client choose access point 3 instead, and now it will get the highest amount of throughput that is possible in this scenario. That's the...
So access point 2 in your picture here was already experiencing degraded throughput. And was that degraded throughput, are you basing that solely on distance, or are you basing that also on the fact that there was a foreign access point that was causing that degraded throughput? Because if there was degraded throughput caused by the foreign access point,
right,
then client 1 would have already seen it.
It's hard for the client 1 to see it before joining it. It can, of course.
But somehow he knew that the throughput was already at 20, well, you changed it, it was at 36 Mbps.
Right.
At 36, was that 36 due to the fact that foreign access point was already there?
The 36 is what it thought it would be. That's the only way of estimating for the client is based on the distance. So it saw the RSSI from AP2. It cannot see what is the traffic on a foreign access point, right? It can only see the beacon strength from AP2. Based on that, it determines that I can connect at this MCS, this modulation and coding scheme, and if I use that, I'll get 36 Mbps. But what is the fraction of time that this access point will get the channel? That is a hard to determine kind of a thing for the client.
But isn't this sort of problem already something that's been identified in things like auto rate function and so on, where if we solely rely on signal strength, we're going to make the wrong decisions.
Right.
And so,
yeah,
as a community, we already have addressed that problem.
So the auto rate function is certainly helping, but it's not a part of the association process, right?
You can't associate.
But so it's not part of the
Client
association.
1 could see, oh, he could get 54 by auto rate, right? Because when the channel's good, it's quite good. But in fact, right, the channel access is kind of taken away by the foreign AP.
So there certainly has been a lot of work on
Average
this.
rates will be bad.
So I think the answer to my question was that the 36 was due to signal strength estimation.
Right.
All right, and that's
Yeah.
what you're considering.
Right.
Okay.
Yeah, that was the baseline sort of a signal strength only case. Whereas this 24 is brought about because the time is divided between the two access points. Whenever it gets the channel, the transmission rate is still 36 Mbps, right? But it gets only half the times, and that's why it's 48 Mbps, but it only gets the channel for half the time. That's why it's now 24 Mbps is the effective throughput sort of. So that's what we wanted to show in this work. So we did a sort of a detailed study on this. The whole idea was to compare the possible gains that are there from this kind of a cooperation in an ideal cooperation regime. The model looks something like this. We have n independent Wi-Fi networks. AI access points in each network, UI number of clients in each network. These are the parameters in the equations. Xij's are the binary variables which say whether or not a client is connected to an access point. Pij's are the fraction of time provided by the AP once it is connected to the client. Rij is the effective bit rate that is determined only from the distance, just the distance based rate. And these BIKs and CIKs are the set of co-channel foreign APs that are present within your carrier sense range and which are right outside your carrier sense range, but which can still interfere with your transmissions. So if we look at that, the optimization problem looks like this. In case of a intra-network, one network optimization, what it tries to do is maximize the utility, the sum utility of all the clients, and the term inside the big brackets here is the throughput of each individual client. And it's determined by its estimate of how many clients are there on each access point and then how many access points are there. Now in case of a cooperative regime, we have a maximization of the same function but over all the networks now. And the additional term that now we can introduce is these information about these BIKs and CIKs, which previously we had no information. They were still there. We had no way of determining what exactly is the value. So now this is the benefit of inter-network cooperation, that we can exactly know what these are and then determine more exactly these values. So these
Who has the PIJs? Where do they come from?
So essentially
Not B, P.
The P's, yeah, the P's are simply 1 over the number of connected clients. The assumption is if an access point has 5 clients, it will time share the channel between the 5 clients, not rate share it, but equally give equal time to each client.
But could you also then go a little bit, and that PIJ that you're saying would be shared with whatever agent is doing the optimization, correct? So an access point will share with whatever optimizing agent that you're my 10 users and I'm going to allocate 1/10, 1/10, 1/10, right? But for that same sort of idea though, you could have the access point say, well, I do know I have a neighboring foreign access point,
Right.
and therefore divide that 1/10 by another factor of, multiply by another factor of half, since I'm going to have to also share with
Right.
the other guy.
Yeah, so that is a reasonable approach. I think the problem with that is it is hard to identify how many access points you have in your neighborhood, and even if you, so you can measure the beacons, you can have a list of beacons, but the exact topology matters as well, and that's something I'll show in the next half, that you cannot guess that you will get half, and if for example if you have one other beacon present, you cannot say that you will get half of the spectrum. You might get 1/3, you might get almost 0, depending on how the topology is created. Only if you have a global view of the whole system, of the whole graph essentially, you can make those kind of estimations. So in this, that's the benefit of having explicit kind of a coordination. If you assume that everyone measures it and sends it, that is a passive sort of a coordination approach in which, yeah. So these equations turn out to be highly non-linear integer programs, but luckily they boil down to a known problem which has an approximate solution, and in particular the cooperative case sort of decomposes into components that each network can solve on its own. All it needs is the information about the BIJs and the CIJs, and it does not need to be a central controller that solves all the problem. It can still be solved inside individual controllers, and we did simulations on this with 2 to 6 overlapping networks, and the standard assumptions, downlink only, no priority kind of clients. this is what the example deployment looks like. This is a two network red and blue kind of a scenario. And in this example, these are what the performance numbers look like. We have a least distance rule, we have an intra-network optimization rule, and a cooperative regime. So what is the client CDF of the client throughputs in each of the three different regimes. We see that on the median scale there is a little bit improvement when we go to cooperative optimization, but the main benefit is for clients which were not performing very well. So one way of looking at it is previously 90% of the clients had more than 220 kbps, but now 230 kbps, and now 90% of the clients have more than 550 kbps. So the bottom line is affected quite a bit if we go to this kind of approach. So that's some benefit of cooperation there. Now we had some more results with a couple of different scenarios in the thesis, but I'll move on to the next problem if there's more questions. So in this problem we are looking at the question of can this spectrum coordination help in the process of channel selection. The secondary question though that we are looking at is also this peculiar phenomena that we are seeing, that initially Wi-Fi access points were mostly low-cost residential APs, at least a vast majority of it. But of late, especially from 2009-10, we are seeing a large number of enterprise or service provider deployed access points. And these guys have $40,000 worth of controllers sitting behind their access points. Now the question is, in the wild, these residential access points and the controller backed access points are playing on the same spectrum. So is it all gloomy for the residential access points? Does that mean that there will be less throughput for the residential access point because the enterprise ones are pretty smart at what they are doing in terms of algorithms? So that's the secondary problem that we tried to address here. What is the mix, in a mix scenario, what does the performance look like in terms of channel selection?
Do residential people actually engage in channel selection?
That's one of the problems, right? So the assumption I'll make about the residential is either fixed channel or the auto setting in which it does a static scan of number of beacons. So actually that is the next slide. Essentially this is what the residential one does, either manual, which is fix and forget, and second is automatic, which you use a crappy algorithm like this where you, upon boot up, this is what you do literally, and it's still the Cisco access points still do this.
Yes.
To this point, right? So you have a list of channels, you see how many beacons on each channel, and you select one channel which has the least number of beacons. The question of course is the number of beacons a good estimate for what your performance will be like?
How often does it revisit?
Never. That's the
only
boot up
Only boot time.
Only boot.
So if you have a power failure.
Yeah, then
Yeah,
you-
perfect. But that's completely wrong because then it's the question of who came up first, right? Whichever access point comes up first, that one will get the
Then the one who
choose any
comes in
channel.
second will choose a different one. That
Yeah,
will-
so eventually you will iterate to some state. I don't know which one.
It'll probably be chaotic because everyone will be coming up around the same time.
Right.
Yeah.
That's
As
one.
long as it's random, it'll
Yeah, exactly. That's what I was gonna say. Random is okay, right? As long as they don't do something bad.
So if you are having trouble with your Wi-Fi, just boot it up again. Maybe that will fix it. Maybe it will select a better channel. But what we are trying to show here is that it is not enough to work on the basis of what you observe on your own. And we did some orbit experiments to prove that point. So in this, these are actual Linux box nodes, 3 of them in this scenario, where the client and the access points are very close to each other. They are right next to the channel between them is very good. But the channel between these pairs, that is what will vary in these experiments. So in this case, they are all far apart, and that's why they can all use the spectrum even though they are all on the same channel. In these two cases, from AP1's point of view, there are two other access points present. But what it cannot know is whether these access points are in range of each other or not. There's absolutely no way of knowing it at AP1. But it turns out that that is what matters if you look at AP1's throughput. It can vary between close to 3 or very close to its equal share, like about 10. So the point here is something that you cannot observe does matter in your own throughput. And just to press that point a little bit more, these are 4-node experiments in which this is the baseline where they are all far apart, and then these are all 4 scenarios in which access point 1 sees 3 other access points. If you notice in each of them, there are 3, the degree of access point 1 is 3 in each of these, but the throughput, look at the throughput that it gets. It's widely varies. It's almost 0, 0, somewhat okay, and in this case, it gets about 9 Mbps. So the graph matters a lot. And the other point is that it is impossible to estimate the channel just from your local observation. So that's the main observation here. And it turns out there was a sort of seminal paper in 2010 which addresses this exact problem, that if you give me a graph, or the interference graph, I can tell you what is the estimate of the normalized throughput or the channel access time that each node will get. It is a very simple to explain kind of a thing. So if you take a graph like this, one of the graphs from the previous slide, you find the maximal independent sets, which is nothing but a set of the nodes in which no two nodes share a link, right? So you can either choose 1 or 2 and 4 or 3 and 4, right? You take these 3 sets, then you only keep the maximum independent sets, which means the sets with the maximum number of nodes. So you keep 2, 4 and 3, 4. Then you find out how many times a node occurs in these maximum independent sets. So node 1 occurs 0 times, so its estimated throughput is 0 out of 0 over 2, which is 0. 2 and 3 occur 1, so it's 1 over 2, 1 over 2, and 4 occurs both the time, so it's 1. And these are the normalized throughput. And if we go back and see, this is very close to what we saw, close to 0, about half, and this is the same rule applies to really large networks as well. They also, this paper goes through sort of a detailed reasoning behind why this approach works so well. It is based out of theory of how CSMA works essentially. Right. So the problem, although, is that finding out this maximum independent set itself is one of the most well-known NP-hard problems. And even to do this, even for like a decent sized networks, it's computationally prohibitive. So we proposed a parametric approximation technique for doing this kind of approach in especially for channel selection. It goes something like this. So let's say this is a graph of the network that you want to estimate the throughputs for, and you want to estimate what is the throughput that node 1 will get. You define something called a span, which is essentially the degree to which you will go outside from that node. So if your span is 0, you will only look at your own viewpoint. So as to, in other words, this is the same as the least channel congestion scheme that I described. You will only see how many beacons can you see, and then assume that they are all connected. I do not want to assume anything about the connectivity of these nodes, so I'll assume they are all connected. This boils down to the same assumption as the least congested channel. So in the span 0 case, it is exactly same as the known LCCS scheme. But if you want better results, what you can do is increase your span. Now you will take into consideration the graph. You will cut the graph at one hop away, and you will again use the same node joining rule to now, for example, introduce this 5-6 link. Right? It wasn't there, but now we add it because there's no way of us knowing whether it was there or not if we cut the graph at this point. So we can estimate, and then we can use the MIA scheme that I just described to find the throughput and so on. We can increase the span, and with full span we can have the whole graph and then compute the MIS. There is a big trade-off when choosing this span, and this shows that trade-off. The top left one is the mean error percentage, and this is the evaluation time. So the key point is when you increase your span, you decrease the error to some degree, but then you also increase the amount of time it takes to compute these estimates. In particular, if we go from 20 node topologies to 30, 40, 50, we see that there is a large amount of error even with span 2. Especially a thing to notice is the deviation is pretty high, and these are averaged over 1,000 runs, and still it's very high. So it says that it is very topology dependent, but still on average you can reduce the errors if you increase the span. But you pay a price in terms of computation time. So you can choose depending on the size of your network what you want to do. Right. So in most of our work in the next few slides, I'll use span equal to 2. So we then proceeded with a two-step approach on how to use this. First, we proposed a correction phase based out of this MIS methodology, and the second is we used it for studying the problem that I described in the first slide, that how do APs in a mixed environment look like what do their performances look like.
Were you assuming that all these wireless LANs were operating at the same fixed rate? Because if one's at 54 and the other's at a different rate, then their radio ranges and your topologies might not be consistent.
So these graphs can be considered like a, let's say I am always assuming that the transmit power is fixed. So now if your transmit power is fixed, it doesn't matter what the rate is when you transmit from yourself to another client, because this line will appear if your transmissions can be heard by node 3. That's the only thing that matters.
Define what you mean by can be heard.
Can be heard means it is above the threshold that node 3 uses for declaring the channel as busy.
So it's carrier sensing.
Carrier sense
Carrier
range.
sensing, so it's just raw power. It's not decodability or anything.
No, that's the raw power. So you are in carriers. If you are in carrier sense range, both of you cannot use it simultaneously, and that is when a link exists. In reality, of course, it is not that black and white. There are regions in which you are out of carrier sense range, but there is still some interference from nodes. But it's very hard to characterize that, and the region of that is also very narrow.
There is also capture.
But the critical thing for my question is all nodes are using the same power then.
Yes, they are.
And power is what affects channel sensing.
Yeah.
Yeah, so when number of nodes are very large, then span equal to full, is it giving very good advantage?
It's so that is the best you can do, but the problem there is the time that you will take in calculating the estimates will be huge. For example, in a 50 node network, if you use full span, it can take about 100 seconds to compute the estimates. You will have very accurate estimates, but it will take you a long time.
Those nodes in your picture,
Right.
those are representing access points.
Yes.
And so if I have a client that's on the edge of my, I guess, hearability range,
Right.
all right, he could still be he could still be heard by you. And so when he's talking to me, he's still causing interference to you. So my interference might not matter to you. It's actually my clients who could also cause.
Yeah. That's one of the things we wanted to extend this to. The reason why we and most other papers start with the access point interference graph model is most traffic is downlink. So most of the times it is the access points which are transmitting and the clients which are only replying with ACKs, with the TCP ACKs mostly. So the amount of time that someone will interfere with me is less compared to what the interference will be like if I am in your interference range, right?
I'm not entirely sure of that argument.
This is downlink only.
Downlink. So she's on the edge of she's associated with me, she's on the edge of my
Right.
range. You and I, though, through this scheme have chosen the same channel,
Right.
all right, and Yvonne is on yours and we're both downloading Netflix, all right. You're on channel 1, I'm on channel 1. She's going to see his Netflix interfering with her Netflix.
No, but that is your APs. You are not going to send while he's sending. He's not going to send while
No,
you're
so
sending.
if we are far apart, yeah, that is a typical hidden node scenario
Yeah,
in that
exactly.
case. Yeah, so in those circumstances, the channel selection cannot help you in that kind of a scenario unless you have that explicitly built into your system. So if you have client positions or built into the scenario or built into your algorithm, you cannot select channels. There can be other ways of preventing that from happening. But usually even in the controller deployed things, it's very hard to do anything based on client positions. They can vary, first of all. Secondly, it's hard to determine where exactly the clients are located. So at least since channel selection is not something you do on a very fine grain, you select channels maybe once every hour at most, because there is a penalty that you pay when changing channels. So that you have to do based on your overall deployment, not where the clients are.
But I just want to make one thing sure I understand. There is no hidden terminal in AP coordination. You can have hidden AP, but there's no hidden. I mean, that's what I'm trying to.
Yeah. That's exactly.
There's no hidden terminal. Downlink doesn't see a hidden terminal. You can have hidden AP, but not hidden terminal. Because the assumption here is that link means APs can hear each other.
Right.
Regardless of where the clients are.
Yeah. So my
and
point
most
is,
of the transmission
I couldn't
is
hear him, and so I make a decision.
No, but you have to. You're an AP. You always hear. That's the link.
Yeah.
The link between two. If there is a link, you always hear each other.
Right. The link in his graph.
Yes.
His interference graph. But it really begs the question of where did I get that topology from? Because if he's far enough away, I don't actually know he's here.
Yeah.
But
So,
we're going to make decisions that are
so
gonna,
building a topology is a separate story.
Right.
okay.
Right.
Yeah. Yeah, so before I go on describing it, this is the baseline algorithm that is mostly used, both in at least one of the products, commercial products, and in most of literature. It is based out of a popular degree of saturation algorithm, graph coloring algorithm, and it works something like this. You start with a node which has the highest degree from your interference graph. You color that node first, and then you update the degree of saturation of all other nodes, which just means how many nodes around it are already colored, and then you color the next nodes in that order. You select the highest degree of saturation node and you color them first, and then finally you have this kind of a coloring, And then if you have to restrict your colors to only the channels that you have, you'll have to recolor the channels, and that will make this graph into 3 separate graphs, which are on now 3 separate channels. So these 3 nodes are on one channel, these are on another, and these are on another.
What does saturation mean?
Saturation is a loose term, which means how many APs around me have already chosen colors. So how many, what is my degree of flexibility in some other words. So if I already 2 channels are blocked for me, because I have one neighbor which chose channel 1, another one which chose channel 2, I cannot choose 1 and 2. So I am pretty blocked already. So I should be selected first when picking up nodes. So that's the rough idea. And so the improvement that we played around with is this simple extra step. So after you are done with choosing the channels, you look at each node. There are 3 nodes here. You look at each node and use the MIS method to test whether these nodes will be starved or not. So if it gets 0 throughput, so we saw that some nodes are getting 0 throughput based on the graph. So if that is the case, we'll try to reassign it to one of the other channels and then check whether we have created a problem for other nodes or not. And if the case is that it can be improved, the whole scenario can be improved, we change the channel for that node. So example, this node, we moved to this channel and we removed it because it was in the middle here and it was getting close to 0 sort of a throughput. So that's the whole idea here. In the simulations we test 4 of these channel assignment schemes. The random, where each AP independently, just uniformly randomly chooses a channel. Local, where it is the least congested channel algorithm. The centralized, which I just described, this degree of saturation. And the 4th is the degree of saturation followed by this correction phase. And essentially what it means is you build you drop the access points. This is the graph that you obtain. Then you use one of these channel assignment schemes, which result in, for example, if you have 3 channels, it results in 3 separate graphs, one for each channel. This is all the APs on channel 1, this is all the APs on channel 6, this is all the APs on channel 11, and so on. So the simulations, some details about them. The area was about exactly 1 square kilometer, and we had only APs in the simulations, no clients. We focused on then the access time that an AP gets, not the throughputs. It's a proxy way of getting at the throughputs. And then we assume downlink saturated traffic and a CS carrier sense range of 100 meters. The metrics that we chose were, first of all, mean normalized throughput, which is, as I said, a proxy for the throughput of all the nodes connected to the AP. And the second thing is the percent of starved nodes, nodes which are theoretically close to 0 throughput, which means in reality they are topologically vulnerable nodes. In reality they might still get some throughput if the other nodes stop transmitting for a while and so on, but it's better to not have these kind of nodes. So these are the first set of results. We compare random, local, central and MIS. This is the normalized throughput, this is the percentage of starved nodes, and we increase the density of access points right from 100 to 500 access points per square kilometer. We see that centralized schemes give us about a 30% improvement over random scheme, and the gain from MIS, this correction phase, increases as the density increases. So when it was 100, there's not much gain at all, but at this point there is substantial gain, about 20% gain there. In terms of the number of starved APs, the improvement is much more visible. It improves that quite a bit, so about 30% reduction in that, and it helps in all densities. There is a gap in the 2 lines throughout. So that's the gain if we go through this approach. Next, what we looked at is mixed scenarios, what I described. So in all these plots, and I have a few of them coming after this slide, the the axes are the ratios of centralized versus something else. So centralized versus random APs. On this edge, it is all random, 0% central. At this end, it is all centralized. And in between, it is different mix. So 25% are central, 75% are random. And these are different densities, and the shaded region is the standard deviation around the solid line, which is the mean. Right? So in this case, what we see is in a mixed scenario, things can improve from a total no cooperation regime to a full cooperation regime. So this is the improvement on the table. That is the max we can get. If everything was cooperating completely, this is how much we will benefit, about 40% in terms of throughput, and much more in terms if we are counting the number of starved nodes, right? So similarly, in this case, the comparison was with random channel selection. In this case, it is with local best decision, and in this case, the gains are a little less, about 15% gain for the 200 access points per square kilometer case, and about 70% reduction on the.
So why do you actually care about starved APs if the aggregate throughput is still good?
Because we do not want to have access points which have close to 0 channel access time. So
couldn't they just be turned off?
Yeah, I mean, if you have a separate scheme running which identifies the starved APs and then turns them off, then you can do that. But the assumption here is the network manager is deploying these access points because it wants to use them, right? So it did not foresee that some of them, just due to how other access points are located, will be starved, right? So ideally you do not want even one access point which is in a bad topology. So it is a metric which might be important, because then even if a client connects to you, it will get close to 0 throughput.
So what's the definition of starved?
Starved is based on the MIS estimate. It gets 0 throughput. It does not appear in the MIS, the maximal independent set, even once. In reality, it would mean is it will only get the channel access when other nodes happen to be quiet, not because it can fight on an equal footing and still get the channel. Only when the other nodes are quiet for a while, it can get the channel. So in heavy load scenarios, you will actually get 0 throughput for starved APs. Right. And this is the worst case sort of scenario in which the comparison is with same channel selection, in which every access point selects the exact same channel, which is quite close to the reality. If we see the number of access points in channel 6, it is heavily skewed. So it's like 50% of all residential access points are in channel 6. And we see that there's a large gain to be had. And the other thing which this graph shows is, it is good news from the perspective of the problem that we pose, that as we move towards completely residential APs to gradually improving to completely cooperative kind of APs, the gains are gradual. So everyone gains, right? The picture is a little more interesting if we break down the performance of these APs into two cases. One is what is happening to the independent APs and what is happening to the APs which were already cooperating. So we break down, so the black line, this black line is the same as this line from before, but now we are breaking the performance into two pieces, for cooperating APs and for the independent APs. And this is interesting that we see that as the number of APs which are coordinating increases, the throughput of the APs that are coordinating decreases, and the throughput of the APs which are still independent increases, right? So in some ways it says that as the world gets smarter, the people who remain non-smart, they have something to gain, right?
It's kind of the opposite of the U.S. economy in some ways.
Well, yeah.
I'm not sure.
This actually is, I came across several works in economics which explain something like this. For example, there is a roommate philosophy of some sort where if you have 3 roommates, then the person who has the most problem with being untidy in a house is the person who has to do most of the work. And essentially what it tries to say is as the situation improves, the person that is the laziest of them all, it improves the most for them, because then they did the least amount of work and they got the best, because other people are now mending their ways. So I am still allowed to be the way I am. So that's like the way in this
The same theory as the worst drivers were all dead before traffic lights, but now traffic lights are saving the worst drivers. Who occasionally kill good drivers.
Similar professor theory about group projects. A team of 3 is always the slacker, who's the 3rd one, and the other 2 cover for him. So
Yeah, he gains the most.
he gains the most, yes.
But he didn't learn anything.
Yeah, so if you really look at it,
That's not a metric that's involved in any discussion.
it's not an important metric. So if we want to stretch this result a little bit, we can say that it is good news for the residential APs in some sense that they will not get very crappy channels as more and more things become very good at selecting the right channels, because there is still improvement for them. We
You
did.
could point out that residential doesn't imply independent, right? Residential can also participate in a group.
That's true, yeah.
As a matter of fact, now for Comcast, it's pretty much all coordinated. I mean, I don't think they have a controller, but they're all essentially tied to the same network, and they could easily be controlled.
So what are they doing?
They're doing nothing, but I'm saying they're doing nothing.
What's changed? The access point that shows?
So if you really look at, if you have that Xfinity or whatever they call it now,
Yeah.
you can actually use your neighbor's access point without any problems,
Oh,
or even go somewhere else,
But
which
they're not
means that the
doing-
backend is the same, right? They go all to the same
But they're
backend.
not doing channel selection.
Nothing. They're doing nothing on the
But
management side.
people's homes are getting access points labeled Xfinity that are at
Well,
public Xfinity.
Yeah, you can
Yeah,
go,
really?
no problem, yeah.
And
They're using it as part of what they call their global
so
deployment.
does this thing, is it kind of like, is it displaying as 2 access points, one in your home and as an Xfinity?
That's actually a good question. I never tried it, but.
No, I could be curious.
I think that's what is happening. So one of the ways in which they offer it is they give you the access point for free if you agree to
serve.
to have 2 SSIDs broadcast from your network. One is your own and the other is, and you can set what is the amount of time.
For you and
What's the share
the
of
share.
And somehow it keeps the partitioning of the network separate, it doesn't let the...
It's
I'm not sure about that. Okay,
At least it
You're
says-
very suspicious of it.
I am.
But
I don't
they
think they
claim
will.
it'll keep you
They,
on your...
what they claim is this, that no outside users will be served as long as you are on the network. Only if you are not using, so only the spare capacity will be given to outside.
Is there something written up on that somewhere?
I'm sure there is
Really small print in your contract.
yeah, I'm not sure about the contract though. But I don't think it's even there. But I know that they give.
Yeah.
I mean,
I've been wondering for years why they weren't doing that.
Yeah,
But
nobody's concerned.
they are.
Well, the other thing is that a lot of the home-based APs now are actually tied to the DOCSIS modem. It's just one box.
Yeah.
So in theory, they have a central point where you can actually do all the coordination because it's all one device.
Yeah, but they don't go as far as doing any real management. It's more just user management and access control.
So
That's the only thing they're doing.
in France, for example, for years a company called Free was disputing their own access points, and at some point of time they said we have enough coverage now that they launched a cellular service, and 5% of all of France shifted to their service because it was so cheap. So they were offering all the full package, the voice, data, messaging, all through their Wi-Fi access points from their residential broadband customers, pretty much free for them. So the next part of the thesis was doing some orbit experiments to validate these sort of results. The setup that used is somewhat interesting. We used the Orbit Sandbox 4, which is, in my view, one of the most underappreciated tools that we have in the lab. It is a very powerful thing that we can use due to the fact that in this sandbox we can program the attenuation between every pair of nodes. So what you can do with that is build an arbitrary graph without having to move a single piece of hardware, without even having to go there. So for example, if you want to build a graph like this, all you have to do is set the right numbers in the matrix. AP3 and 4 are not connected, so what you do is AP3 and 4, you put a high attenuation there. So there is no connection now between AP3 and 4. So with this, we can easily and quickly build several different topologies and play around with how they behave, how different channels selection schemes behave in different topologies. We did 2 experiments with this. One is a 5-node experiment for doing this comparison. One is an 8-node experiment. That's the max number of nodes, by the way, on the sandbox. So the 5-node experiments look something like this. We first created all possible 5-node connected topologies, and there are 21 of such topology possible. We created each one of them and then tested what the channel selection schemes result in each of these topologies. So by the way, each topology means there is an access point and client on each node essentially. So these are the connections between the access points. And this is what the results look like. The graph is a little cluttered, but it has a lot of information on it. So the y-axis in each plot is the throughput. The x-axis has no meaning except it separates the points out. It's just for separating the points out. It is not dependent on any variable. So, and each box is one of the topologies that I showed. And then these dots are, the pink ones are for random, blue for local, and the black for MIS. So we see overall the big picture here is that local is better than random and MIS is better than local, as we can see. But also it is highly topologically dependent. In some cases, even with MIS, some nodes are still not very good. For example, in this one, it's still halfway mark. In this one, it's below. In some cases, all nodes are now really good. So it is somewhat topology dependent. Overall, things look like this. The overall throughput is 10 Mbps, about 13 and 16 when we go from one to the other. So that's it matches the trends, at least match well with the simulations that we had. This is the other experiment that we did, the 8-node experiments, and with 8 nodes it turns out there are more than 11,000 topologies possible. We selected 100 of these at random.
You didn't do all 11,000?
And I couldn't get the orbit for that.
The time, yes.
Yeah.
It'll take forever.
Yeah, and luckily because of the way the sandbox is set up, I could automate the whole process. So all I have to do is select, input the topology, and the whole experiment runs on its own. I get the throughputs back and then just plot it. So for each topology, I do 9 set of experiments. In each one of them, I vary the number of APs which are under central management from 0 to 8. And these are the graphs, and the trends are very similar to what we observed from the simulation results, that as we increase the percentage of nodes under central, overall there is improvement, and there is also improvement for the independent nodes, and there is some decrease in the throughput of nodes which are already centralized. So that's the rough idea is that the trends match the simulation results pretty closely. This is the final part of the thesis.
I have one question. So, in that last graph,
Yeah.
so if here you sort of assume the traffic is the same across,
Right.
if the, say, for example, the residential had much lower traffic, and the commercial or the coordinating ones had, much higher traffic,
Right.
Would the benefits sort of change? I mean, is it still beneficial to coordinate a lot?
It will depend on a lot of things, I think. So one is you can base your channel selection also on the load. And in one of the examples I'll have later, I'll try to do that. In this scheme, your channel selection process has only the graph as the input, no load information. But you can take the load also under consideration when you do this. But the other question, as you said, is what is the benefit of AP which has very less load? What is the incentive for it to coordinate? And I think that is, it can be said that there is always a benefit, even if you have less load. What is the amount of benefit? That can vary, but there will always be scenarios in which even for the less load that you had, you will not be able to transmit that amount of traffic if you select the wrong channel. So there is always some incentive for you to cooperate. Yeah, so this is the latest part of the work where we wanted to go ahead with realizing these kind of inter-network cooperation regimes, actually writing code and getting things up to speed on that. The results we have is very simple baseline sort of a API which describes how two controllers should talk to each other. The flow of the scheme is the following: that first you want to discover who your neighbors are. Once you find a new neighbor, you want to exchange a coarse level of information with them, which just gives you enough information to determine whether or not you want to cooperate with that person. If you determine that there is a need for cooperation, you can request for more specific information from the other controller. For example, what is the channels on these APs that you control, and things like that. And finally, if then you can do your own calculation, then you can send specific commands like request channel change on this AP and so on. Now the whole thing is very subject to sort of deployment specific features and so on. It's very hard to come up with the definitive API which everyone will agree to, but this is just a start. And these are some of the structures that we defined. This is the initial coarse-grained information structure, and this is the fine-grained structure where we have the IDs, the frequency, time, and spatial domains. And these are the 9 message types like cooperation request, accept, info request, accept, and change parameter request. Just a simple basic set of things that you need to get started. And we went ahead with some orbit 2 network experiments with this kind of approach, where we have a Python script running on 4 APs which were controlled by one of the controllers, and the other 4 APs in the experiment were controlled by another controller, and there is a controller script that is also running. And the specific topology that you want to set, you can again set this using that matrix method. And the idea is that at some point of time we want to make these controllers talk to each other and see what is the gain when they do that. This is the scenario that initially each network sets the channel on its own, and at time 25 seconds it's a 60-second experiment. At 25 seconds, controller B provides info about the load of all the APs to controller A. And this is an example scenario in which the channels are determined based also on the load on the channels. So each AP, when it starts, it selects or its load is chosen from a uniform random distribution, a UDP kind of load between 5 and 45 Mbps. So these are the example load scenarios, and then the channel selection is such that the total throughput that each AP gets is highest, depending on the load and the graph both. And this is a slide video of how things look like. So when we start, each one of them gets whatever throughput it gets based out of its own channel selection. At time 25, controller A reselects the channel and it changes it for two of the nodes. As you can see, AP4 and AP8, the channels are changed, and as a result of it, the throughputs of several nodes are improved. Actually, two of them in particular. Node 1 goes from this level to this level, and node 8 also the throughput improves for that. So that's the very basic result sort of, which shows that we can actually write code which can result in improvement once you start coordinating with each other. And of course, a lot of work has to be gone into it to remove this period of zero throughput, for example. We don't want this region in which no one is getting anything. But it can happen in real time that we can change channels and improve things. So that's one of the latest results, and some of the ongoing sort of future looking work on this angle is we want to go one level deeper into this. We want to, in order to have this inter-network collaboration, one thing that I think is needed is we need to slightly change the way in which the wireless control plane is architectured. It's a software engineering problem, most of all. We have to open up the control plane in some sense. So this is what the current controller sort of looks like, where a lot of control functions lie not just in the controller but also in the access point and also the client side devices. For example, some of the rate selection, power selection schemes are at the access point side, not at the controller, because they require fine-grained things. Now, if we want these inputs from other networks to really be used for everything, all the control plane things, we have to centralize all the control plane elements. We have to take out the decision-making part of all the algorithms and push them into one central place. At that place, we can have other inputs from other networks and have a cooperation scheme, and all that is left then in the access points and the clients will be the actions. So the action taking part will still have to be at the AP side, but the algorithm, the decision making part will have to be at the controller. So that's where this work is going. We want to leverage the SDN line of thought into this kind of approach, and we have some initial ideas. This is what Ivan and I were working of late, a control switch kind of a infrastructure where when you have this kind of a scenario in which all the control is separated, in that kind of scenario, how can you direct the control messages into different points, into your own controller, into a controller of a neighboring network, so that you can do all those optimizations that we described, and that's the current sort of set of things we are working on. I guess, yeah, that brings us to the last slide. That's the conclusion. So the overall scheme of things have been to advance the state of art in cooperative or coordinated dynamic spectrum access. We looked at and developed two specific scenarios in which cooperation can help a lot. In the client AP association case, we saw that we can have up to 140 to 170% improvements in client throughputs. And for the channel assignment part, we can see up to 4x reduction in staffed APs and about 40% improvement in the client throughput. Also, we are currently extending the work to have a more holistic SDN-based wireless control plane implementation. So that's the gist of the whole thesis. This was the work that I described at the start. I've been able to get a few publications out of each one of these different works. This was part of my master's thesis. This was one of the patents filed during the internship. This was the later publications on this topic. And on the mobility first side of things, a few publications on that as well. And most important part, would like to thank Professor Ray. He's been just an amazing advisor. I couldn't have asked for a better work culture, to have a more relaxed environment at all. It's one of the reasons I stayed back, did my thesis, was to have a cool advisor like Ray. Thanks a lot, Ray. Would also like to thank my committee members, Roy, Wade, Jennifer. I've bugged you all a lot in the process of coming up with the ideas, so thanks. And this would have not been possible, which goes for most theses around WinLab, without the help of Ivan Seskar. So thanks a lot, Ivan. And my family was mostly in India, been very supportive of throughout this whole 6 years. My really awesome lab mates with whom I've spent a lot of time, and my super awesome friends, I've spent probably more time with them than working on the thesis.
The lab mates are now feeling a little hurt.
Maybe there's
Professor overlap.
Yes, I was just going to say, maybe there's an overlap. I don't know, right?
Yeah.
So I guess they're not naming them.
That keeps it safe. Right? Always, oh no, but you were here. You know?
Then you have to find
Each
the
one will be like,
maximum
I'm
size.
probably in the super awesome.